we need two textbooks. One is for thermodynamics, fundamentals of engineering thermodynamics, 9th edition, and the other is, what is the name? Oh, right here. Fundamentals of Heat and Mass Transfer, 8th edition by Bergman. I think you got an email from the bookstore that you have an inclusive access. If you don't like that, you can get a refund. You can cancel it because we don't need that, any function in online. I just heard that they are cheaper than buying a hard copy. So this is just one of the options. If you want to have a hard copy, that's totally fine by me. You can get them online. You can get them from Amazon or anybody who already graduated from this school. I think there's a 2 weeks window that you can get a full refund. If you don't like that online version, you can get this hard copy. If you want to have an older version, that is also fine by me. If you find the 8th version or 7th version, they are cheaper. That's also fine by me, but you need to, to find a rich friend who has the latest version because the homework assignments are based on the latest version. Okay. Same goes to this heat transfer book. So we need two textbooks. I think the first one is the same book in your EGR456 Thermodynamics 1. So if you have it, it's good for you. If you don't, then find somewhere. Okay? Or you can just use that online version on Blackboard. That's also fine by me. I just heard that it's cheaper. I don't know. Okay. There will be 3 tests, 30% of each. The first test is going to be after we complete thermodynamics 2. So this course is designed, and this course covers 2 different subjects. One is thermodynamics 2, and the other one is heat transfer. In most, the engineering course, these 2 are separate courses. However, in this course, we combine them. I don't know, maybe trying to make it as challenging as possible. So don't hate me, but it is just the way it is designed. So it's going to be really tough. It's not one of the toughest courses. It is the toughest course in this school. So be prepared. Don't hate me. That's not me. That's how it is designed 15 years ago. So the first task is going to cover thermodynamics. So we are going to study 2 chapters. One is gas mixture, the other one is combustion. So the first exam is going to cover these 2 chapters. Of course, to learn about these 2, gas mixture and combustion, you need to, remember, you need to recall the fundamental thermodynamics that you studied a long time ago. But don't worry about that. I will spend maybe 1 or 2 weeks to review those materials, okay? And the second test is going to cover conduction heat transfer, which is going to be 2 chapters, chapter 3 of this book and chapter 5 of this book. We're going to talk about that after the first exam. And the last exam is not comprehensive. I don't like comprehensive exam. It's too much work to do within a short time frame. And this course is very challenging, so it's not comprehensive. It's going to cover 1 item that is convective heat transfer that covers chapter 7, 8, and 9. Okay, we can talk about that after the second exam. Okay, so each is going to be 30%. Those 3 are pretty, not similar. So if you fail in the first exam, don't worry about that. The first exam, goodbye. And the second, the material is going to be pretty new. So you can do a fresh start, okay? Sounds amazing? No? And homework assignment, 7%. If you remember my previous EGR456, you remember that the homework assignments are going to be submitted online. So write down your solution to the problems anywhere with piece of paper or somewhere on the table, and then take a photocopy and then convert it to PDF and upload. If you prefer to do it, on a Word file or any software, that's fine. Just please convert to the PDF. Compress it as much as possible, because I remember last year there was one student always upload 1 gigabyte PDF that takes 20 minutes to download. It's too much. Sometimes my computer just stopped while downloading. That's not funny, okay? So convert to PDF. If you do not know how to compress PDF or how to create PDF, there's lots of websites. One of the examples is going to be ilovepdf.com, or you can go to any of the computers in university. We have a site subscription to Acrobat Pro, so you can create any PDF and compress it as much as possible. Please do not, upload 20 different PDFs. You can combine them, okay? And there will be a 3% is going to be attendance. I'm going to check attendance maybe one or twice, one day, random day, when I see the least number of students. That's the judgment day. If you remember, if you watch the Terminator 2, the judgment day, right? Okay. So that is going to be 100%. If you miss any homework assignment deadline, that's okay. Late assignments will be accepted, but there will be a 20% penalty. So don't send me an email that, I totally forgot about the deadline, can I still submit? Yes, you can, but there's a 20% penalty. But no late work is accepted after the final exam. I want to go to winter break, okay? So that is the final day you can submit any missing work, okay? So first 2 weeks, we are going to review thermodynamics 1. It's pretty nice, right? So we are going to study chapter 3, first the law of thermodynamics, chapter 4, second law of thermodynamics, and chapter 5 is second law of thermodynamics, and up to none of the applications, entropy and open system, those the materials that we need to study the gas mixtures and conversion. So the review is going to be 2 weeks, and there are 2 chapters, gas mixtures and combustions. These are very challenging subjects because we are applying the same mass balance equation, energy balance equation, but we are trying to make it a little more complicated, because in thermodynamics 1, our system was dry air. However, in reality, the air in this classroom is not dry air. If it is dry air, we don't like that because it's too dry. But in reality, we have the humidity. So that means that we have the air in real world is going to be dry air and water vapor mixture. So we are going to, use water vapor dry air mixture as our working gas, which is going to make your thermodynamic analysis very complicated, because there will be lots of new parameters that you need to study such as relative humidity and the humidity ratio and etc. And there will be another the steps to evaluate the properties of dry air and water mixture. It's going to be time consuming and also the complicated. And the combustion, we are going to talk about the chemical reactions between two different materials, and to do so we are going to use a molar analysis, which is different from the mass analysis that we did in thermodynamics 1. In thermodynamics 1, we know all the calculations were based on mass analysis, mass basis, which means that there was 1 kilogram of oxygen, there was 2 kilograms of water, steam, etc. But when we go to combustion, we are going to study everything on a molar basis, which means that we had 1 mole of oxygen react with 2 moles of nitrogen. No, they don't get we had 1 mole of nitrogen react with 2 moles of oxygen. Then now that we have a chemically sound. And then we are going to also study a balancing reaction equations, how two different materials are going to react. There are rules that we need to follow. Those are the things that we are going to study in the advanced thermodynamics section, which is going to be covered by the first exam. Okay? Then there are 3 different heat transfers: conduction, convection, and somewhere here, radiation. Conduction means that when you have a hot cup of coffee, when you hold it, you feel that it is very hot. How do you feel this is very hot? Because there is a heat transfer from this cup to your hand, your skin. So that is called conduction. The heat is transferred to the material. That's a conduction. So we are going to study this conduction in the many different ways, like the one-dimensional heat conduction, the two-dimensional heat conduction, steady-state heat conduction. That means that outside is pretty hot, inside is pretty cold because we have AC is running. Then the temperature outside remain constant, temperature inside remain constant. That means that steady-state heat conduction. Then we are also going to talk about transient heat conduction. When there's a heat transfer from this coffee to my, the hand, the temperature of the coffee goes down, then the properties of this coffee changes with time. That is called transient conduction. So we are going to talk about one-dimensional, two-dimensional, and steady and transient conductions. All together is going to be covered by your second exam. And then third is going to be convection heat transfer. Convection heat transfer means that we have a heat transfer mainly due to mass transfer. What does it mean? If it is windy day outside, then when the wind blows, then you feel that it is chilly or sometimes hot air. It is hot. That heat transfer is not mainly due to the material. It is more carried by the mass transfer. When there is a mass transfer involved, then it is called convection heat transfer. There are 3 different convection heat transfers. One is the forced convection, external forced convection, and internal forced convection, and natural forced convection due to gravity. So we are going to study these 3 modes of heat transfers and convection heat transfers that they are going to be covered by the final exam. If we have time, we are going to study the last mode of heat transfer, which is radiation. And mainly, you can expect that the radiation, one of the examples of the radiation is the solar radiation. When you go outside in one of the summer days, you feel that it is hot. You don't want to stay there anymore because that is the radiation heat transfer. Radiation heat transfer means that it transfers in the form of electromagnetic waves. Therefore, there is no material is involved. It's not like you are holding one end of this copper rod and the sun is holding the other end, transferring heat through these copper materials. It's not like that. Okay? So that's ready. So this is pretty much about the overview of this course. And any question? Yes.
Will you be recording your lectures like you did in Thermo 1?
I am doing it now, but I already did the last lecture this morning, and turns out the quality is pretty bad. Because I usually go with my the headset and my phone. Somehow there is a technical glitch in WebEx. So the voice, the only way I can record my the lecture is through this mic. I don't trust it. But I listened to my previous video that I recorded this morning at 9 o'clock. It's not good. But I will keep doing, but don't rely on that. Okay. But that's a backup. Okay? Just in case you miss it because there was a so if you miss it, you can rely on that, but the quality isn't good. Okay. But yeah, we will provide. Any other question? How was the summer? No? Good? Really? No. The summer was pretty hot here. I think the hottest summer in Michigan, right? I feel like that I went back to Texas. I lived in Texas for 10 years and then tired of it and then moved to this Michigan, right? Now, the last summer was like summer in Texas. I don't want to go there. I don't want to go back. It's too hot. Now it is getting hot. So should I find a new job in Canada? Okay, so to study thermodynamics 2, we need to review what we did in thermodynamics 1. We are not going to cover the entire chapter. We are going to focus on mass balance and energy balance equations for two different systems. One is closed system, the other is open system, and finally, we are going to briefly go over entropy. So those three items are what we are going to do, okay? By the way, all the lecture notes and the homework assignments are available on Blackboard. So please visit Blackboard and download anything that you want, okay? By the way, if you think that I'm doing too fast or too slow, just let me know. I will do my best to. By the way, I don't like this class. Can you see from up there? No? Can I hear that? Can you see that? Well, okay. I prefer that, the screen is somewhere in the middle, not on the side. Okay, so we are going to study a few things first. Close the system. So how we can, apply energy balance equation in a closed system, how we can apply energy balance equation in an open system, and also how we can evaluate properties such as specific volume, specific internal energy U, specific enthalpy H for two different systems. The first one is phase change materials, and the other one is pure systems, like the oxygen, nitrogen, or water, liquid or solid. And we are going to talk about entropy S, so how we can evaluate them too. and how to solve entropy balance equation, which is going to be chapter 6. So we are going to study how to evaluate a property and how to solve energy balance equations for closed system and an open system, and finally entropy. So let's talk about how to evaluate phase change in Fourier. To evaluate a property of phase change in Fourier, we first need to remember the 5 phase change processes. So mainly we focus on the phase change transition between liquid and vapor. So when we talk about phase change between liquid and vapor, we can make property diagrams such as TV diagram. When you make TV diagram, let's assume that this is water at 1 atmospheric pressure. Then the boiling temperature, which is saturation temperature, T sat at 1 atmospheric pressure, is going to be 100 degrees Celsius. Then, if we have liquid water at 20 degrees Celsius, then to undergo phase change, we can heat this water. If you heat this water, when pressure remains constant at 1 atmospheric pressure, so pressure is constant pressure. P is constant. Like our real life, if you want to boil water, what we do is that, we heat the water at this constant pressure, which is 1 atm. Then, initially, water exists as compressed liquid. Here, compressed liquid, a substance that it is not about to vaporize. And if you heat this water, its temperature goes up from 20, 30, 40, 50, 60, 70, and there will be one moment when the temperature of the water reaches the saturation temperature, T sat, which is the boiling temperature. That brief moment is called saturated liquid. So we have a compressed liquid, this much, number 1. We have a saturated liquid. It's going to be a very brief moment. If you heat this water, which is currently just as saturated liquid, its temperature does not go up anymore. Instead, phase change occurs because that's the saturation temperature. And any extra heat, any additional heat to this water is not going to increase the temperature anymore because that's the saturation temperature. Instead, there will be phase change from liquid molecules to vapor molecules. So when there's a phase change from liquid to vapor, its volume goes up because the density of liquid is much, much greater than the density of vapor, right? And therefore, when you heat this water, then more and more liquid molecules vaporize. And eventually, there will be one moment every molecule in the system is in the vapor phase. That is called saturated vapor. Phase change process number 4, saturated vapor. When you have liquid and vapor together between, it is called saturated mixture. Phase change process number 3, saturated mixture. When you boil water on a stove, you see bubble is forming from the bottom, right? That is saturated mixture. You have a air and you have a vapor and you have a liquid water together. Then what is the temperature? When you have a saturated mixture, 100 degrees Celsius. So we use this, the saturated mixture, when you want to calibrate any temperature sensor. At 1 atmospheric pressure, we have a temperature thermometer, and you are not sure that if this one is showing the accurate temperature value. And the simplest way you can do is that you can boil water and then dump in your thermometer into it. If it shows 100 degrees Celsius, that is correct because it is saturated mixture. The temperature should be the saturation temperature, right? So once every molecule in the system vaporized, then it is saturated vapor. Any additional heat into this vapor is not, the induced phase change anymore because there is no more phase change. Everything is in the vapor phase already. So now the temperature goes up, which is superheated vapor. Number 5. The heat transfer, the amount of heat, the heat transfer, while it is compressed liquid, is called sensible heat. The heat associated with temperature change. So sensible heat means that the heat changing the temperature of a system. And the heat which is going to change the phase is called latent heat. So this red is going to be latent heat. And we have a super vapor, which is again an additional heat is going to change the temperature. So that is sensible heat. So sensible heat and latent heat together, we call them thermal energy, right? So thermal energy consists of 2 different energies. One is sensible energy, the energy associated with temperature change, and the other is latent energy, the energy associated with phase change. So that is the overview about 5 phase change processes. 1, 2, 3, 4, 5. Now, the next thing that we need to know is how to evaluate a property of a system. It depends on the phase change process. If you have so there are 5 different phase change processes. Number 1, compressed liquid. That's one. Number 2, saturated liquid. Number 3, saturated mixture. Number 4, saturated vapor. Number 5, superheated vapor. There are for water, there are 1, 2, 3, 4 different tables that we are going to use. If you have So this is for water only, okay? H2O. Like water, like the water that we can drink. Is there heavy water? Yes. The water that we use for nuclear power plants. What is the difference between light water and heavy water? Heavy water you cannot drink. It has one more nutrient, and in order it can survive at higher temperature, so you can pressurize your system more. That will increase the efficiency. But anyway, this is light water. So there are 4 tables that we are going to use to evaluate a property of a phase change material. They are, this is for water, okay? Table A2, properties of saturated water temperature table. This is the table that you use when you know the temperature of a system. And number 3, properties of saturated water pressure table. This is the table that you use if you know the pressure of your system. What about if you know pressure and temperature, both of them? You can use any of them, right? And table A4, this is the table that you are going to use when you know your system exists as superpoint vapor. And one more property to go, table to go, that is the table A5, properties of compressed liquid water. This is the table that you use when you know you have a compressed liquid with one condition. That one condition that we are going to talk about it later. Then going back to this table, we have, going back to this graph, we have this TV diagram. That means that using this TV diagram, you can understand temperature with volume, no, specific volume relation. In this TV diagram, number 2 is saturated liquid. Number 4 is saturated vapor. The properties of saturated liquid and saturated vapors, and so the properties of these 2 points are directly available in a table. So if it is saturated liquid, its volume is going to be VF. If it is saturated vapor, its specific volume is going to be VG. So when you see a subscript F, that means it is the property of saturated liquid. If you see a subscript G, that means this is the property of saturated vapor. If you know you have saturated liquid or saturated vapor, you will see either subscript F or G. They can be found from the table. So if you have a saturated liquid, if you want to determine V, it's gonna be VF. If you have a saturated vapor, if you want to determine V is gonna be VG. Then, on what table? If you know temperature, you can go to the temperature table. If you know pressure, you can go to the pressure table. According to this TV diagram, it says the pressure is 1 atmospheric pressure. So anywhere on this line means the pressure of the water is at 1 atmospheric pressure. So if you know the pressure which is 1 atmospheric pressure, then you can go to this table, pressure table, table A3, pressure table. So let's go to the pressure table. So here is the pressure table, and 1 atmospheric pressure. One atmospheric pressure is close to it is 101.325 kilopascal. That is 1 atmospheric pressure. That means the pressure at the sea level. Then, what is the unit in the property table? The unit of the property is bar. What is bar? The place you can drink. No, bar is a unit of pressure, and it is close to 1 bar is 100 kilopascal. So 1 bar means 100 kilopascal, 2 bars means 200 kilopascal, and etc. Then 1 atm is 101 kilopascal, which is close to 100 kilopascal. So you can say 1 atm can be considered as 1 bar. Then, to determine the properties of saturated liquid and the saturated vapor of this water on this TV diagram, which is at 1 atm, not automatic teller machine, it's atmosphere. You can go to this table, and there is 1 bar, which is close to 1 atmospheric pressure. So if you want to determine specific volume of saturated liquid, which is VF, so you see this subscript F, its value is going to be available here. And VG, saturated vapor, it is also available here. So if you have saturated liquid or saturated vapor, and you know its pressure, then you can use this table to determine their properties. One thing you need to be careful is the specific volume of saturated liquid is pretty small. So the actual value is going to be 0.001. To make it simple, we multiplied the specific volume by 1,000 and wrote them here. So the actual value is going to be this value divided by 1,000. Okay. So you can find these two directly from the property table. What about, I do not know the pressure of our water system, but I know the temperature of the system. Then you can go to the temperature table, such as this one. You can go to the temperature table. If the temperature of the water is 10 degrees Celsius, the specific volumes of saturated liquid and saturated vapors are available in these two columns. Okay. Then you may have another question, which is, okay, for specific volume V, I get that if we have saturated vapor or saturated liquid, you can find them directly from a table. What about other properties, such as specific internal energy U or specific enthalpy H, or specific entropy S. How do we determine them? It's not that difficult. Specific internal energy U is gonna be UF. Specific enthalpy H is gonna be HF. Specific entropy S is gonna be SF. What about this property diagram? Oh, property diagrams are also very similar. For example, if you know the pressure of your system, so let's say the pressure is 200 kilopascal, then you can make what diagram? If you know pressure, then you can make temperature diagram. If you know pressure, so that means that your water is at 200 degrees Celsius. Do we make pressure diagram? No, we already know pressure. Why do we study pressure, right? We know pressure and we don't know temperature, so we make temperature diagram, right? So the temperature diagram is going to be T something. It can be temperature T V diagram, not the television, or TU diagram, temperature specific internal energy, TH diagram, or T entropy diagram. They all look similar. So they all look like this. So on this T, V, T, U, T, H, T, S diagram, we have two reference points. Here, saturated liquid, phase change process number 2, or here, saturated vapor number 4. And the properties at these 2 points are going to be Vf if it is TV diagram, or UF if it is TU diagram, or HF if it is TH diagram, or SF if it is TS diagram. So you can make TV diagram, looks like that. TU diagram looks like that. TH looks similar. TS looks similar. Okay. What about number 4? It's the same. VG, UG, HG. HG sounds familiar. Printer. Oh, that's HQ, right? No? HP, right? No? Oh, HP, right? Oh, HP, not G. My bad. Monday thickness. It's Monday for me because this is my first day at school. Yesterday was holiday for me. So you can make T, S, T, H, T, U, T, V, depending on the what property you are interested. So let's say that you know a pressure of your system and you want to know specific volume. You want to know U, H, S, depending on what you are interested, you can make T, V, T, U, T, H, T, S. And here is going to be compressed liquid, here saturated liquid, here saturated vapor and superheat vapor. Similarly, if you do not know the pressure of your system, you can make another diagram, assuming that you know temperature. So temperature, let's say that I know the temperature of our water system. Can I make a property diagram? Yes, why not? Since we know T, What is going to be the vertical axis? Pressure P. So at this temperature, we can study pressure and another property relation. It can be either PV, PU, pH, or PS. And let's assume that if it is PV diagram, then the graph is going to look like this. The upside down of this TV graph. So going down this way and this way. So here we have saturated liquid, saturated vapor, and this is compressed liquid, saturated liquid, unsaturated vapor, and superheated vapor. And these 2 points can be found, can be determined directly from a property table. They are VF, VG, UF, UG, HF, HG, and so on. Is it too fast? No, it's good, right? Because this is not new. You already studied them last year. I'm doing a quick review. It's not that quick, so let's do it a little bit quicker. So, if you know that you have a saturated liquid or saturated vapor, then there's not much thing that you need to worry about because you can find them directly from a property table. So number 2 and number 4 were easy. What about the next? Number 5, when you know that you have superheated vapor, then it's pretty simple. You can go to superheated vapor table, table A4, compressed properties of superheated water vapor. That's table A4. So I can say table A4. What was the tables for saturated liquid and saturated vapor? If you know temperature, table A2. If you know pressure, table A3. If you know temperature, table A2. If you know temperature, pressure, table A3. What if your system exists as saturated mixture? Then there's a problem. This mixture can be, in any ratio. So the mixture means that you have a saturated liquid and saturated vapor together, right? It can be mixed at 10 to 9, 1 to 9, or 5 to 5. So 20% liquid, 80% vapor, or 30% liquid and 70% vapor. So depending on the ratio, you may have a different properties, right? So to evaluate a property of saturated mixture, you first need to know what is the mixing ratio between liquid and vapor, right? So we need to know new parameter that is called quality X. Quality X. Quality X can be determined by the mass of vapor over mass of liquid plus mass of vapor. In other words, the total mass. So if you have 1 kilogram of water and 0.4 kilograms of that water is in the vapor phase. That means the quality X is 0.4, right? So the quality X has a value between 0 and 1. Quality X 0 means you have no vapor. You only have liquid. Means saturated liquid. Quality X is 0. What about quality X is 1? That means you only have vapor. So saturated vapor is 1. So the ratio X to quality X is will be between 0 and 1 when you have saturated mixture. So that quality X is the number one thing that you need to determine whenever you have saturated mixture. Then let's assume that you already have the quality X. Then how can we evaluate a property such as VUHS? If you know the ratio between two different values, you already know the values of these two. Then you can simply use linear interpolation to determine a value between these two. What is the equation? Linear interpolation. It's simple. If it is specific volume V of saturated mixture can be determined by VF2 plus quality X times the difference between VF and VG. VG minus VF. So this is the linear interpolation equation to determine specific volume V of a saturated mixture. What about if it is not specific volume but specific internal energy U? Then you can replace this V with U. U is UF plus X times UG minus UF. What about H? HF plus quality X, HG minus HF. What about entropy S? SF plus quality X times SG minus SF. So these are the linear interpolation equations to determine property of saturated mixture. That means that you already have to know the property values of saturated liquid or saturated vapor. The last one is compressed liquid. For compressed liquid, it is a little bit weird. If it is compressed liquid, there are two ways to evaluate the properties of this. One is when pressure is high enough. When pressure is high, how high? If you go to table A5. By the way, the PDF version of this table is also uploaded on Blackboard, so you can download and print them out. So if you have a compressed liquid, if the pressure is 2.5 megapascal, you can use this table. If the pressure is 5, you can use this table. 7.5, this one, 10, and so on. What about pressure is between 2.5 and 5? Let's say pressure is 4. Then you can do a linear interpolation between these two numbers. Okay. Then, and by the way, the lowest pressure value in this table A5 is going to be 2.5. Why is that? Above or equal to 2.5 megapascal. How high is it? What is the pressure in this classroom? Approximately 100 kilopascal. in megapascal, 0.1 megapascal. 2.5 megapascal is 25 times higher pressure than this cluster, which is pretty high. So when pressure is this high, the properties of compressed liquid changes a lot. Therefore, we need a table like that. So what about pressure is not this high? Then the effect of pressure on the properties of compressed liquid is negligible. So we don't consider. Then how can we find their properties? We assume that there is no effect on from pressure. Then we only rely on the other property. What is the other property other than pressure? Temperature. So we can evaluate the properties of compressed liquid only based on the pressure. Only based on temperature. So is there any liquid that we can evaluate its property? Yes, saturated liquid. When pressure is low enough, in other words, less than 2.5 megapascal, we assume that the properties of saturated liquid and the properties of compressed liquid are the same. As long as they have the same temperature. So only the temperature is the dominating, the properties in this case. So when pressure is less than, what is the criteria? 2.5 megapascal. We assume that if you want to determine V, okay, V, we think that that is the same as VF. VF, but at what condition? The same temperature. T, not pressure, temperature. What about U? UF at the same temperature. H, HF at the same temperature. S, SF at the same temperature. So what does it mean? If you want to evaluate their properties, always go to the temperature table, not the pressure table, temperature table, because our assumption is there's no effect of pressure when pressure is not that high. Then what about pressure is high? How high? Equal to 2.5 or greater. Oh, then we have a table, A5. So this one slide shows everything. It's a summary of how do we evaluate a property of a phase change material. Any question? Then what we are going to do? We just heard it, so that's it? No, we are engineers. So we like to practice. So let's practice problems. So we learn. So I'm going to solve this table, and that will be all for today. Complete this table for water, H2O. You may remember this table. Let me just recall you. So the table consists of 5, the things: temperature, pressure, specific enthalpy H, quantity X, and the phase change process. So the table only has 2 property values, then you are going to evaluate all the others. Okay? Each row represents a table. Each row represents a problem. So they are independent problems. So there are total 5 problems. So let's look at the first problem. in this first problem, we have, by the way, this is also in your, the lecture notes. You can download on Blackboard the review PPT or something. So this time we know pressure. So if you know pressure, what do you want to do? You need to make a property diagram, right? So let's say, that I know pressure that is 200 kilopascal. I'm going to make a property diagram. So what kind of property diagram? Since we know pressure, we are not interested in pressure anymore because we already know. Then what is the other, the important property, temperature T? And as I showed you earlier, you can make TV, TU, TH, and TS, anything, they all look similar. So, which property diagram do you want to make? TV, TU, TH, TS. H, because H is the one that you need to determine. Okay, you're right. So I'm going to make TH diagram. TH diagram looks like what? Here, this way, okay? So I'm going to make TS diagram looks like this. What does it mean? When you have water and the pressure is 200 kilopascal, your water should be always somewhere on this T. What about here? Oh, I think my water is right here. That means the pressure is not 200 kilopascal. Then is the pressure greater than 200 kilopascal or less than 200 kilopascal? Less than. One easy way to understand is that what is the temperature? This temperature. Saturation temperature. So which is the boiling temperature in our real life. So the boiling temperature, if your system is below here, that means that the saturation temperature is lower than here, right? So when the boiling temperature goes down, when pressure goes up or pressure goes down? Pressure goes down, right? So if your system is below this graph, means that pressure is less than that. If your system is up there, means that the pressure is greater than this. Okay. So there are many things that you can learn from this property diagram. So we know on this TH diagram, there are 5 phase change process starting from 1, 2, 3, 4, and 6, right? No, 5. Here we have HF. This F, the subscript F represents saturated liquid. This is HG. The printer? No, that's HP, right? And what is HG? HG. Huh? Oh, right, mercury. Oh, yeah, thank you. So that's a saturated vapor. Then, based on this TH diagram, let's solve it. Okay, so I just made this TH diagram. Oh, what is the other property that we know? I know quality X. Quality X is 0.7. 0.7 means when the quality X is between 0 and 1, that means we have phase change process number 3, saturated mixture. Because the quality X is the ratio between liquid and vapor. If it is between 0 and 1, that means that you have a liquid vapor together. So currently your water is boiling, right? So I can say this is phase change process number 3, saturated mixture. Then, how do you determine the temperature? So, you have a saturated mixture. Where is it? Right here, number 3. So, somewhere on this line, what is the temperature? Oh, do we have a temperature on this property diagram? Yes, this vertical axis is the temperature. Okay, so the temperature we are looking for is here. Then let's go back to the summary slide. What is the temperature on this horizontal line? That is called T-sat, saturation pressure. So the temperature should be the boiling temperature. So what is the saturation temperature at 200 kilopascal? At 200 kilopascal, the unit of this pressure in the table is bar. 1 bar is 100 kilopascal, and therefore 200 kilopascals is 2 bars. Where's 2? Oh, right here at the bottom. At 2 bars, what is the saturation temperature? 120.2. 120.2 degrees Celsius. So that is the saturation temperature. I'm going to write it here, 120.2. And the last one that we want to determine is H, specific enthalpy. Then let's go back to the summary slide. We have saturated mixture. How do we determine H? We can use this linear interpolation equation, HF plus X times HG minus HF. Let me write them down here. H is HF. Let me write it here. H is HF plus quality X times HG minus HF. So let's see. Do we know HF? Oh yes, HF is here. This one, 504.7. Do we know the quality X? Yes, 0.7, that is given, plus 0.7 times Hg. Hg is here. So the number we are looking for is 2706.7 minus HF again. We already got that, 504.7. So if you solve it, you get H value. That goes into the table. Do I know the value? I don't know, but you have a calculator, right? Any question about this first problem? No question, right? It's too easy, isn't it? Okay, if you don't have a question, let's go to the second problem. On this time, again, if I go too fast, let me know, okay? On the second problem, we have temperature T and specific enthalpy H. So if you have temperature T, what do you want to do? I know temperature T, 140 degrees Celsius. I want to evaluate a property of this system. The number one thing that we need to do is make either this diagram or this diagram. Since we know temperature, we can make pressure diagram, right? So I'm going to make a diagram that is pressure diagram P something, but what something? Again, H, because we know H. I'm going to make TPPH diagram. pH diagram, according to this summary slide, looks like this. So I'm going to copy and paste. Copy and paste. On this pH diagram, we have number 1, number 2, number 3, number 4, and number 5. And there are two important properties. They are HF, HG. So let me just say that this one is P set, saturation pressure. So once you know temperature, should come right there, right? So once you know temperature, if you want to evaluate this water system, you need to first make pH diagram. And there are three unknown properties, P set, HF, HG. You need to find them. From where? From this temperature. So let's go to the temperature table. Right here. Temperature table. Where is HG? 140 is right here. What is the pressure? 3.61 bar. However, 1 bar is 100 kilopascal, so this is 361.3 kilopascal. HF is here, HG is here, so we are looking at these two properties. 589.13, 27, I'm sorry, you cannot see that. 27, 33.9. So once you find these values, now we are ready to solve this problem. Okay, so by using the temperature value 140, I just made pH diagram. Now let's look at the other property that we know. What is the property? H. H is 1800. So where is H on this pH diagram? Oh, there it is. The horizontal axis is H. So let's find 1800 on this axis. 1800 is greater than 589 and less than 27. So should be somewhere in the middle. So what is the phase change process? Number 3, saturated mixture. Then you can write saturated mixture. Then what is the pressure of saturated mixture? So you have, your system is right here. So what is the pressure? Do we have pressure on this diagram? Yes, this vertical axis. So what is the pressure? P set 361.3. 361.3. Now, the only missing is 40x. Since we know it is saturated mixture, let's go to the summary table, summary slide. We know that this saturated mixture, is there any portion that contains X? There is X. So you can use this equation to determine X. So let me write this equation here. H is HF plus quality X times HG minus HF. What is the H value of our system? 1800. Do we know HF? Yes. 589. Do we know HG? Yes. 2733.9. Do we know HF? Yes. 589. We have everything. Can you determine quality X? Yes, we can. That's how you evaluate properties of the second problem. It's about time, so on Thursday, we are going to continue this table and we are going to find the other three, and that will be all about finding a property of phase change material. Okay? That's all. Any questions? No? Okay, then see you on Thursday.
I have a question for you. So you went to Texas A&M for your doctorate?
Yeah.
So do you know if they have a good aerospace master's program?
They have an aerospace engineering, yes.
Good.
Not bad, not
I
bad.
went to University of Texas and
Okay.
University of Florida
Okay.
and Embry-Riddle.
What about